Let's continue with tools for visualizing numerical variables now. The simplest one of these tools is what's called a rock plot, which shows, as we already mentioned earlier, the distribution of a single quantitative numerical variable. We can see how to make a rock plot by loading, in this case, let's take a look only at the birth weight data. So this is a column which, as we saw earlier in our data set, the birth weight was a numerical variable. There's a few others, but let's concentrate. Let's focus on the birth weight. We have 1100 of these, and we can make a rock plot just by calling the Seaborn rock plot function. The problem with rock plots is that they're not by themselves particularly easy to extract too much information from there. They tend to be useful as part of another figure. First of all, they make poor use of the entire plotting area, but they also tend to lead to a phenomenon called overplotting. So, for example, if we wanted to ask the question, how many birth weights are there around 120? It's very hard to tell. We know that there's close to 1,200 points being plotted here, but obviously we see a lot less than 1,200 individual bars. Now, if we could zoom in a lot, maybe we could zoom in enough to start counting, but from the entire plot by itself, we can't really tell that. So when we want to look at a little bit more of the structure of numerical variables, histograms, which you already saw in data 8, are kind of the starting point and the standard workhorse. What we do in a histogram is to smooth the data, to aggregate the data in order to more easily, by looking at aggregates and summaries, to more easily get an understanding of the data set. So what we have in a histogram is effectively a smoothed version of a rock plot, where the horizontal axis is the number line, but divided into bins. And the most important point to remember about histograms is what do they represent, and this is something that you already know from data 8, is that what we see is the proportion of the data that corresponds to each bin, and that fraction is equal to the width of the bin times the height of the bar. Now, keep in mind, this should be already, you should be thinking of calculus. The width of the bin times the height of the bar, that is an area, and that says that areas represent proportions, and the notion that the total area should add up to 1 or 200% is exactly the visual representation of the histogram of the notion that a probability density should integrate out to 1. And so these two things are completely related, and you can think of a histogram as a discrete rectangular approximation to the density. From a calculus perspective, you can think of it as an Euler version of the numerical integral for the distribution. So how do we make histograms? Well, Matplotlib has a default histogram routine. So if you have a set of numbers, you can just call plt.hist, and you get a default histogram. It will automatically compute the range. We can see that the range is properly computed. This is the minimum and the maximum of this particular data, and it gave us bins that cover that range. And we can see that by default, it picks some choice for bins. It doesn't have a specific hard-coded value, but it picks a choice. It turns out that the choice of bins is sum of how many bins you have and where they are is somewhat arbitrary. Let's say, for example, that we wanted to choose bins between 50 and 200, but in widths of 5, so slightly thinner bins than these. What does that do to the histogram? Well, if we look at, this is the same data, right? This is the same data, but plotted with different bin sizes. In this case, this was the default that Matplotlib used automatically, and in this case, we've made our own choices with bins. It turns out, as you make your bins smaller and smaller, you're aggregating smaller chunks of data, and what you see in the data will be a little bit different. The notion of there being an optimal choice of bin size is actually one that has been studied statistically, and we'll revisit it in a moment. But the general rule is that you should try to have a reasonable number of bins that gives you enough detail into the data that isn't too coarse, but not so small that in general your bins have very, very few data points in each on average, because at that point you're basically falling into the extreme, if you will, of a ROG plot, of something kind of close to a ROG plot. Now, exactly how to compute kind of that happy medium we'll come back to in a moment. Now, one important point, though, is that by default in Matplotlib, a histogram isn't showing us proportions. It's showing us by default just counts. How many points are there in each of these bins? Whereas if we actually want a proportion, what we need to ask for is for the histogram to be computed as a density, and for that we can use the density keyword, and in that case you see that the counts get normalized so that now we have proper proportions. And what I want to do next is a few simple calculations with histograms. We can see from this particular version of the histogram that has counts instead of proportions that there were close to approximately 120 babies born with weights between 110 and 115 pounds. And remember, we have about 1,200 observations total, give or take. So the question is, how can we compute that if we are looking at a proper histogram that has been appropriately normalized, as we saw a moment ago in the notebook? Once we actually compute it with the density equals true, how could we figure that out? So if we remember the formula about what a histogram represents, first we keep in mind what is the total number of observations, and now we ask, well, what is the width of the bin? These bins are width 5 each, and keep in mind that this is an open-ended interval. So in the case of this particular data set, the baby weights are all integers. So this would contain baby weights 110, 112, 111, 12, 13, and 14. But the baby weight 115 would be included in the next bin. So baby weights of 115 would be included here. Now, the height of the bar is just from looking at the plot, it's roughly 0.02. And so if we multiply the width of the bin by the height of the bin, we get the proportion of the data that is contained in here, which is 0.1, which means about 10%. And about 10% of this is 117, give or take. And that was exactly the number that we had before. I mean, up to the fact that we're doing this calculation just by eyeballing these values quickly. So obviously this is information that we had in the data, but it is important for you to know how to read a histogram, and to know that if you know the complete size of the data set, you can recover count information from a properly normalized histogram in a pretty straightforward manner. Now, be careful about drawing too strong of a conclusion from the look of a histogram, because as we saw before, you have a choice over the bin size, and the number of bins influences the appearance of the histogram, and there may be features that you think are important in the data that disappear if you choose a different bin size. Now, there is a statistical criteria called the Friedman-Diaconis rule. David Friedman was a Berkeley, a very well-renowned Berkeley statistician, and Percy Diaconis is a colleague of his who's still at Stanford, which is to choose the bin width as twice the interquartile range, which is the difference between the 25th and the 75th percentiles in the data distribution, divided by the cube root of the number of points. Now, this formula may look a little bit strange. The paper that derives it is fairly technical, but the point is that it is the optimal bin choice as long as you make certain statistical assumptions about the relationship between the data you're looking at and there being an underlying distribution that produced that data. Since in general, when we're looking at real-world data, we don't exactly know what perfect statistical distribution produced the data, this particular rule may not be optimal. It may not be perfect, but it is a rule of thumb that you can use, and that is very easy to implement with the tools you have available now. So if you want to make sort of a statistically optimal choice under certain assumptions, you can use the Freeman-Diaconis rule. You can play a little bit with just by hand as you make your plots with bin widths, but in general, as I said, it's important to keep in mind that you shouldn't, if you think that you see some particular feature, change the bin sizes a bit, move them, wiggle them around a little bit, and see if that feature disappears if you make them a little bit coarser, or a little bit finer. Because if that's the case, then it was just an artifact of how the data was falling around particular bin edges, rather than something which is genuinely in your distribution. Now, you may actually encounter histograms that have unequal bin sizes. It's not very common, but it's perfectly valid to do so, and the libraries let you do that. So if you ever encounter a histogram like that, keep in mind the importance of thinking in terms of areas and proportions, so that you make your interpretations correctly. Now, instead of histograms, we can visualize what a continuous smooth distribution corresponding to that same histogram would look like. This is what's called a density curve, and out of a discrete histogram we can create density curves. Today we're going to look at how we do that in the plotting with our plotting tools, and later we'll revisit that topic in the next lecture from a more mathematical perspective. So this is just to wrap up how we can get this histogram by calling the same histogram, in this case by calling the plot method on the pandas data frame object, or the pandas series object in this case, and we get more or less the same information. And these are a couple of examples of the code that will lead to changes in bin sizes, or even potentially producing these unequal bin sizes that we saw already. So these are choices that you can make in your own code. Now, how do we produce these density curves? Seaborn has a function called KDE plot that, instead of a histogram, will produce one of these density curves. It turns out that Seaborn actually has several related functions for plotting distributions, and I encourage you to take a look at the documentation. There's kind of an overall plotting function called thisplot that actually dispatches under the hood to KDE plot for these density curves, histplot for histograms, and rockplot for rockplot for making rock plots, and can combine them together. So if you want, for example, get only a histogram, but with the density overlaid on top of it, you can use the Seaborn histplot routine and say, oh, I also want a KDE on top. If you don't produce this, let me show you the difference. If you don't do this, this is what you get by default. So this is the difference, whether you ask for the density curve by asking for the KDE. Now, you can also combine, for example, combine these together by using the thisplot routine. And with thisplot, you can ask for both a histogram with a KDE and a rock plot as well. So in this case, you can get all three in one routine. This plot itself is very flexible. So you can say, for example, I want the KDE and the rock plot, but without a histogram, and you can obtain that by asking the thisplot routine to do so with the appropriate parameters. So again, I encourage you to look at the documentation and play a little bit with these functions to understand how they work. Seaborn has a fairly detailed explanation of when you might want to use this plot, kind of the overall wrapper versus the individual ones, for what kinds of operations you may need one or the other. And we'll revisit this. Now, the mathematical way in which this density curve is computed and constructed is something that we will revisit in the next lecture, because there is a technique called kernel density estimation, and this is why the keyword in Seaborn is KDE equals true for this plot, or the function is called KDE plot, precisely because this is called a kernel density estimator.